Hello everyone. I am Dr.E.Purushotham, Associate Professor, Department of Physics, School of Sciences and Humanities. So, in our previous class, we discussed Schrodinger time independent wave equation, physical significance of wave function, properties of wave function, limitations of wave function. Today, I am going to discuss about particle in one-dimensional potential box. Particle in one-dimensional potential box. So particle in one-dimensional potential box, or it is also known as particle in an infinity height potential well. Infinity potential, infinity height potential well. So you can see here, for example, this is the potential box, potential box. So this is infinity height potential well, potential well. For example, this is x is equal to 0, x is equal to L. L is the width of the potential box. Here also both are same. X is equal to 0, x is equal to L. We can take like this. So particle in one-dimensional potential box or particle in an infinity height potential well. So you can see here, particle in one-dimensional potential box. What are the only one-dimensional? Do you know any one-dimensional related in your everyday life examples? So I am giving some one-dimensional moving, one-dimensional related some examples, daily life examples. You can see here a toy car on the track. You can see in your daily life a toy car that can only move back and forth. And a straight track is confined in one-dimensional. So it can move forward, forth, and back. So it will come. That is the one-dimensional. You can see second one, second example in your daily life at your home, a sliding door in a track. You already observed at any place a sliding door that moves only horizontally within a track is continued to that one dimensional part. And you can also take here a piece of paper in an envelope. Just we are putting in the envelope and we are taking back. That is only one dimensional moving. There is no different x direction and y direction and z direction. Only one directional along x axis or along one direction. A shoe in a shoe rack. We are putting the shoe in the rack and we are taking out in one dimensional. A toothbrush in a holder. We can put on the toothbrush on the holder. We can take same. That is one dimensional. A mouse and a mouse pad. On the mouse pad, we can move like this and we can move like this. A pen in a pen case. A pen in a pen case also we can put like this and we can take like this. A rat in a labyrinth box also. You can see here. So the car is moving forward and coming back. The rat in a box, it can move one dimensional direction. Here also you can see the boy is playing here. So the boy is playing here. The car is moving this side and going back side. This is one dimensional only. We can observe one dimensional. The rat also, for example, it is imagine it can move this side and this side. This is one dimensional. Try to go out the train, the rat. Try to go out in one dimensional. So here also the car is moving toy car this side and again this side. Only we are considering this side and this side. These are the one dimensional related. Already we are observing here. You can see a toy car on a track, one dimensional. A sliding door in a track, a piece of paper in a envelope. a toothbrush in a holder. So these are the daily life one dimensional motion related one. So particle in one dimensional potential box. Particle in one dimensional potential box. You can see here, I am drawing here. So this is the box. I am taking this is box. Just to try to understand here. So this is x is equal to 0. This is x is equal to L. X is equal to L. So this is the potential box. We are considering the particle motion along the x direction. Along the x direction. So from this place to this place, what is the width of the box? L. Width of the box L. So one dimensional potential well also at infinity height we can take like this. This is infinity height potential well. This is x is equal to 0. This is x is equal to L. Don't confuse, both are same. So this is width L. Width L. So this is closing box. This is infinity height. Imagine infinity height potential well. Consider a particle of mass m. Consider a particle of mass m moving inside a box along the x direction. It is moving along x direction. It is moving along x direction. It is moving along x direction with velocity v. With velocity v. Let the width of the box L. The particle is bouncing. So the particle is moving and incident on the walls. It is bouncing back without losing any energy. The walls are perfectly rigid at x is equal to 0 and x is equal to L. The particle will not lose any energy in collision with such walls. Hence, its total energy remains a constant inside the box. Inside the box, the potential energy of a particle is 0. Potential energy of the box is equal to 0. Here also, potential energy of the box is equal to 0. 0. Don't confuse. So you can see here, this is particle in one dimensional potential box. Particle in one dimensional potential box. What I am saying, consider a particle of mass. So this is infinity height well potential box. I am taking same here, another one box. So I am giving this box. So this is x is equal to 0. This is x is equal to L. A particle of mass m is moving with velocity v along x direction. It is incident on the wall. It is bouncing back without losing any energy. So the total energy inside the box is 0, but potential energy V of x is equal to 0 inside the box. Let us consider a particle is confined to the region 0 less than x less than L along one direction. As shown in this figure, you can see here. So this is the value is x to L, x less 0 less than x less than L. It can move freely within the region 0 to L, 0 less than x less than L. But the particle experience infinity potential at x is equal to 0. You can see here, and at x is equal to L, x is equal to L. Therefore, it can overcross to the right to the region x greater than L or to the x less than 0. It means V is equal to 0 in the region 0 less than x less than L, and raised to infinity V is equal to infinity at x is equal to 0 and x is equal to L. This situation is called particle in one dimensional potential box. Particle in one dimensional potential box. So actually at x is equal to 0, x is equal to L, in between also x is less than or equal to, this is 0, in between x 0 is less than or equal to x less than or equal to L. The potential energy is 0, 0 to L, 0 to L. Don't confuse. This situation is called a particle in one dimensional potential box. Particle in one dimensional potential box. Consider a particle of mass m moving inside a box along the x direction. Let the width of the box is L. You see, width, this place to this place, width is the L. Width of the box. Here also, width of the box L. Width of the box L. The particle is bouncing back. Bouncing back. The particle is bouncing back without losing any energy. The walls are perfectly rigid at x is equal to 0 and x is equal to L. The particle will not lose any energy in collision with such walls. Hence, its total energy remains constant inside the box. The potential energy of a particle is 0 at V of x is equal to 0. At V of x is equal to 0, that is 0 less than or equal to x less than or equal to L. L. So you can see here the one dimensional potential, the one dimensional time independent Schrodinger wave equation we are applying here for a particle trapped in one dimensional box. V is equal to 0 and the Schrodinger equation takes the following form: dou square psi by dou x square, dou square psi by dou x square plus 8 pi square by h square into m e psi. Why we are taking here E psi? Actual Schrodinger one dimensional time independent wave equation, dou square psi by dou x square, A to pi square by h square, E minus V is 0 of psi is equal to 0. So we are getting, this is one dimensional Schrodinger time independent wave equation, dou square psi by dou x square plus A to pi square by h square, E psi is equal to 0, is equal to 0. Or another one also we know very well, another equation, dou square psi by dou x square plus 2m by h bar square into E is equal to 0. E psi is equal to 0. You can take either this equation or this equation. Both are same. This is Schrodinger time independent wave equation in terms of Planck's constant. This is Schrodinger time independent wave equation in terms of reduced Planck constant h bar. H bar. But here, 8 pi square m by h square into E up to this. Let us take that is k square. So I am substituting here. This is dou square psi by dou x square as it is. 8 pi square m by h bar h square, at the place of h square I am taking k square into psi is equal to 0, is equal to 0. Or here also you can take, this is at the place of 2m e by h bar square is equal to k square. This is the main difference in these two equations. Clearly try to understand here. So this is equal to k square. The Schrodinger time independent wave equation for free particle inside the one dimensional potential box, potential energy V is equal to 0. So we are applying the Schrodinger time independent wave equation. At the place of 8 pi square m by h square into E, you take just k square. I am substituting here k square at this place. Or another equation also we derived. This is dou square psi by dou x square plus 2m e by h bar square into psi is equal to 0. Don't confuse. This is also just to take k square. We get equation 3. So dou square psi by dou x square plus k square psi is equal to 0. From this equation also we get this one. And from this equation also we get equation 3 dou square psi by dou x square plus k square psi is equal to 0. K square is equal to 0. So that is equation number 3. Equation number 3. So the general solution for equation 3 is given by psi of x is equal to a sine kx. So for this, what they are writing here, the general solution of the equation 3, this is not a perfect solution. This is imaginary solution. We are taking the general solution. That is psi of x is equal to a sine kx plus b cos kx. This is equation number 4. That is the general solution of equation 3. So, in this equation 4, A, K, B, the constants, this is A, K, B are there. This is A, this is K, this is B, are the unknown quantities. A is the incident amplitude and B is the reflection amplitude. A is the incident amplitude and B is the reflection amplitude. To calculate these unknown quantities, boundary conditions can be used. That boundary conditions are just I am giving first boundary condition. I am giving first boundary condition x is equal to 0 because at the place this is the one dimensional potential box. We are taking this is x is equal to 0, this is x is equal to L. So first boundary condition x is equal to 0, psi of x is equal to psi of x or psi is equal to 0, psi of x or psi is equal to 0, mod psi square is equal to 0. Second boundary condition, this is first starting boundary x is equal to 0, this is final x is equal to L. Remaining same, we can write mod psi is equal to 0 or psi is equal to 0. Mod psi of x is equal to 0. Mod psi square is equal to 0 or mod psi of x square is equal to 0. You can take. These are the boundary conditions. You can see here. So boundary condition at x is equal to 0, psi of x is equal to 0 and mod psi square is also 0. That is the boundary condition. Boundary condition. So applying the first boundary, number 1, applying the first boundary condition. First boundary condition, BC. First boundary condition in equation 4. So what is the equation 4? Psi of x is equal to a sine kx plus b cos kx. So psi of x is equal to 0, first boundary, you can see, is equal to a sine k, x is equal to 0, you can see, plus b cos k into 0. This is equal to a sine 0 0 plus b cos 0 1. What is this? A into 0 0. So b is equal to 1. Is it 1? No. B is equal to 0. B is equal to 0. You can see here. B is equal to 0. Try to understand. So this is step applying the first boundary condition. Applying the first boundary condition. What we will get? So psi of x, equation 4, psi of x is equal to a sine kx plus b cos kx. What are the first boundary condition? I am writing in bracket x is equal to 0, psi is equal to 0. Just to substitute in above equation. So psi of x that is equal to 0. A sine k x and x is 0 plus b cos k into 0. So this is 0. A sine 0 0 plus b cos 0 1 b into 1. A into 0 0. So 0 plus 0 plus b 0 0. This is 0 is equal to, not plus, this is 0 is equal to a into 0 0 plus b. So b is equal to 0. Up to here clear. This is b is equal to 0. Now now substituting b is equal to 0 in equation 4. In equation 4, this is the equation 4 I am writing here. So psi of x is equal to a sine kx plus b 0 into cos kx, that is 0. So psi of x is equal to a sine kx. This is equation number 5. Equation number 5. You clearly observe here. So this is, we got b is equal to 0. Now substituting b is equal to 0 in equation 4, we get psi of x is equal to a sine kx. A sine kx, that is equation number 4. So we get equation 5, psi of x is equal to a sine kx. I am writing here clearly, this is equation number 5. Number 2, second point, applying the second boundary condition. Second boundary condition in equation 5. Second boundary condition in equation 5. So equation 5, psi of x, what is the second boundary condition? X is equal to L. You know very well. For example, this is a box. This is x is equal to 0, first boundary. X is equal to L, second boundary. So x is equal to L, psi of x or psi is equal to 0. So substitute in above equation, psi of x is equal to 0. A sine k, what is x? L. So we can write this step here also, sine a sine kl is equal to 0. Either a is equal to 0 or sine kl is equal to 0. But a is not equal to 0 because this is unknown quantity. We need to calculate a value. But sine kl is equal to 0. Sine kl is equal to 0. Kl is equal to n pi. Kl is equal to, what is this? Kl is equal to n pi. Kl is equal to n pi. You can see here Kl is equal to n pi. You can see this relation here. KL is equal to n pi. From this relation, K is equal to n pi by L. That is equation number 6. Equation number 6. So we cannot take n is equal to 0 because for n is equal to 0, K is equal to 0 and E is equal to 0 and psi of x is equal to 0. Everywhere in the box. This means that particle with zero energy cannot be present in the box. That is, a particle in the box cannot have zero energy. Cannot have, yes, particle. Allowed wave function of a particle in one dimensional potential box. So substituting the value of x in this equation, what is x is equal to n pi by L? We received here x is equal to n pi by L. No, k is equal to n pi by L. K is equal to n pi by L. I am substituting here k is equal to n pi by L. So psi of x is equal to a sine kx. We are substituting at the place of k, that is n pi by L, a sine n pi by L into x. Don't confuse. So we received here, try to understand here. So we are substituting a sin kl. We got a sin kl. A sin kl is equal to 0. Sin kl is equal to 0. Kl is equal to n pi. K is equal to n pi by L. Now we are substituting this k value in this equation. Psi of x is equal to a sin kx. But what about k value? K is equal to 2 pi by k is equal to 2 pi by n pi by L, not 2 pi by L. N pi by L. So substituting psi of x is equal to a sine n pi by L into x. You can see that particular equation here. Psi of x or sin of x is equal to a sine n pi by L into x. So you see here psi n is equal to a sine n pi by L into x. This is equation number 7. Equation number 7. Are you understanding? So k is equal to n pi by L. We calculated. We are substituting in psi of x is equal to a sine at the place of k n pi by L into x. So for psi of x, for n, psi n of x, we can take here n is equal to 1, 2, 3, and so on. So this is a sine n pi by L into x. That is equation number 7. Equation number 7. So we have calculated k value and b value. So unknown quantities a, k, b. These are the unknown quantities. Unknown quantities. We have calculated k value. K is equal to n pi by L. B is equal to 0. We have calculated. So we are going to calculate a value. A value. You can see here. Applying the normalization condition of a particle in a one-dimensional potential box. From equation 5, we know very well this equation. What is that? Psi of x is equal to a sine kx. What about k? N pi by L. We got finally equation 7. Now we are applying normalization condition. We can determine the value of constant a in the above equation 7. The normalization condition. The probability of finding the particle in one-dimensional potential box is called normalization condition. What is normalization condition? The probability of finding the particle in one-dimensional potential box. The probability of finding the particle in one-dimensional potential box is equal to unity. Unity means 1. This is the left side value is the probability of finding the particle in one-dimensional potential box is equal to unity. Unity. So you can see here, for example, this is the one-dimensional potential box. So limits x is equal to this is 0, x is equal to this L. We can take integral of 0 to L limits. So this is sin of x, sin whole square or sin of x whole square dx is equal to 1. This is the probability of finding the particle in one-dimensional potential box is equal to unity, is equal to unity. Now, here substituting at the place of sin of square is equal to this value. At the place of sin, we are taking this one. Sin is equal to a sine n pi by L into x. So this is mod square. This is also mod square. We can take this is equal to a square sine square n pi by a square sine square n pi by L into x. So you can see here a square sine square n pi by L dx is equal to 1, is equal to 1. So here this is a square, this is a square. We are substituting a square integral 0 to L as these limits. So sine square n pi by L dx. So you can see here sine square n pi by L is equal to, we can write 1 minus cos 2n pi by L divided by 2. So you know very well this sine square sine square x is equal to, we can write 1 minus cos 2x all divided by 2. So converting this like this, we can write 1 minus cos 2. This is n pi by L, like this is a x. So this is x, that is 2 n pi by L all divided by 2. What I am saying clearly try to understand. Sin square x is equal to 1 minus cos 2x all divided by 2. So converting this one, sin square n pi by L into x is equal to 1 minus cos. Let this is here x. So 2 I am taking as it is here 2. What is at the place of x? N pi by L into x all divided by 2. So you can see clearly, you can observe without any confusion. 1 minus cos 2 n pi by L into x all divided by 2 dx is equal to 1, is equal to 1. So I am taking here this whole divided by 2, I am taking out of integral here. So a square by 2 integral 0 to L 1 minus cos 2 n pi by L into x dx is equal to 1. 1. So we are going to take here, we are going to take here, okay, up to here as it is in previous slide. So I am taking this one, a square integral 0 to L 1 minus cos 2n pi by L into x dx is equal to 1. So a square, I am taking integration separately 0 to L 1 dx minus integral 0 to L cos 2n pi by L into x bracket close. This is here also dx inside the box dx. Try to see here. So a square by 2 integral 0 to L 1 minus cos 2n pi by L This is x, dx is equal to 1. So a square by 2, I am taking as it is. I am separating integration 0 to L 1 dx separate and minus integral 0 to L cos 2n pi by L x dx separate. So is equal to 1. So a square by 2 as it is. Integral of 1 dx. This is x limits 0 to L minus. So integral of cos 2n pi by L x dx. What we will get? So this is cos 2n pi by L. Integration of cos, what we will get? Sine 2n pi by L x divided by 2n pi by L. So limits 0 to L is equal to, this is closed bracket, and is equal to 1, is equal to 1. So next step, a square by 2, I'm applying the limits. Upper limit L minus lower limit 0 minus. This is L by 2n pi. Substituting here sine 2n pi L by L minus sine 2n pi by L into x 0. So this L gets cancelled. This is equal to a square by 2 as it is into L. This is minus L by 2n pi inside the bracket. This is 0. Sine of 2n pi 0 minus sine 0 0. So 0 into L by 2n pi into 0 0. So this is equal to a square L here is equal to 1. Here also is equal to 1. So a square L by L is equal to a square by 2 into L is equal to 1. You can see here a square by 2 into L is equal to 1. 1. You see here a square by 2 into L is equal to 1. A square is equal to L by 2. A is equal to whole root of L by 2. Now substituting this A value in psi of x is equal to, or psi n of x is equal to a sine n pi by L into x. So from this relation, we will get here psi n of x is equal to, at the place of a, I am taking root L by 2, root L by 2. That is wrong. So this is equal to, here a square is equal to 2 by L, 2 by L. A is equal to root of 2 by L, root of 2 by L. So clearly try to understand a square by 2 into L is equal to 1. So a square is equal to 2 by L. A is equal to whole root of 2 by L. So substitute a value, sin of x is equal to a sine n pi by L into x. So sin of x is equal to a root 2 by L sine n pi by L into x. So you get this equation 9. Sin of x is equal to root 2 by L sine n pi by L. That is equation number 9. That is normalized wave function. The sin of x is known as normalized wave function. Wave function. Okay. So regarding that, the calculation of this total part, you try to understand clearly. I am giving one problem here. I am giving one problem here. So, problem. An electron is trapped in an infinity potential well of length 2 angstroms. In the ground state, evaluate the probability of finding the particle, probability of the finding the electron is the particle, electron in the region x is equal to 0 to 0.25 angstroms. Solution. From the given data, from the given data, width L is equal to 2 angstroms. N is equal to 1 because they mentioned ground state. You can see ground state. This is ground state. Evaluate the probability of finding the electron in the region x is equal to 0 to 0.25 angstroms. So one dimensional potential well, this is x is equal to 0, this is x is equal to 2 angstroms width. We need to find here 0 to 0.25 angstroms. Angstroms. So we know the probability of finding the particle in one-dimensional potential box, they gave limits 0 to 0.25 angstroms. We can write mod psi 1 square dx. That is the probability of finding the particle, right? But we know psi 1 value. Psi 1 is equal to root 2 by L sine n pi by L into x. Substituting all the above values, this is psi 1 is equal to root 2 by L value 2 sine n value 1 into pi by L value 2 into x. That is psi 1. That is psi 1. Now now substituting psi 1 value in this equation 1. In equation 1. So P is equal to integral 0 to 0.25 limits. So mod psi 1 whole square. I am taking here, this one we can modify 2 by 2 gets cancelled. So we can write this is sine pi by 2 x. So sine pi by 2 x whole square. This is sine square pi by 2 x x. We can see here, so P is equal to integral 0 to 0.25 sine square we can write 1 minus cos 2 pi by 2 into x dx and whole divided by 2. So this 2 gets cancelled. P is equal to this half 1 by 2 I am writing outside of the integral. So this is integral 0 to 0.251 dx minus integral 0 to 0.25 cos pi x dx. dx. So P is equal to half integral 0 to 0.25 1 dx minus 0 to integral 0 to 0.25 cos pi x dx. So this is equal to 1 by 2 as it is. So integral 1 dx, that is x, limits from 0 to 0.25 minus integral of cos, that is sine pi by pi, limits from 0 to 0.25. So this is equal to 1 by 2. I am substituting limits. Upper limit 0.25 minus 0 minus 1 by 2. This pi I am writing here 1 by 2 pi. So sine of 0.25 pi, here we missed x. Okay, here this is x. Okay, at the place of x, I am substituting 0.025 pi minus sine 0. So this is equal to 1 by 2, 0.25 as it is, minus 1 by 2 pi. So this is sine pi by 4. 0.25, that is 1 by 4 into pi, pi by 4, pi by 4. Okay, we can take here, this is 1 by 2, 0.25 minus, substituting 1 by 2 pi, 2 into 3.14 into sine pi by 4. What is that? 1 by root 2. So finally, you will get P is equal to P is equal to 0.013. Finally, we get 0.013 after calculation. After calculation. So if you have any doubt, you can see here that calculation also 1.1 by 2, 1 by 2 into 0.25, 125 minus 1 by 2 pi sine pi by 4. This one also we can calculate. This is 0.0125, 0.25. After calculation, this is 0.125 minus 1 by 2 pi. This is 1 by root 2. 1 by root 2. So this is 0.125 minus 1 by pi into 1 by 2 into 1 by root 2. So multiplying with root 2, dividing with root 2. 0.125 minus 1 by pi value 3.14. This is root 2 by root 2 into root 2, 2, 2 into 2, 4, 4. So we can get calculation. This is 0.125 minus 0.112. Finally, we get 0.013. So P is equal to 0.013. The percentage, we can take 0.013 into 100, that is equal to 1.3%. 1.3% we will get. That is the answer. That is the, so this h square goes to this side. You clearly try to understand here 8 pi square m e by h square is equal to n square pi square by L square. So you can see here equation. This pi square gets cancelled. From this relation, E is equal to n square, this h square here, by 8m L square. So this is E is equal to n square h square by 8 ml square. Therefore, the allowed energy values are given by En is equal to n square h square by 8 ml square, where n is equal to 1, 2, 3, and so on, and so on. En is the allowed energy levels for free particle in one-dimensional potential box. If n is equal to 1, in this equation, in this given equation, En is equal to n square h square by 8 ml square. If n is equal to 1, just to substitute E1 is equal to, at the place of n, that is 1 square h square by 8 ml square, that is h square by 8 ml square. You can see here h square by 8 ml square, that is E1, energy 1. This energy is known as first energy level or ground state energy level. First energy level or ground state energy level. So E1 is equal to n square h square by 8 ml square is also known as 0 point energy of the system. 0 point energy of the system. So this is the lowest energy level. N is equal to 1, lowest energy level or ground state energy level. For first excited state, this is first excited state, N is equal to 1. So second energy level, that is first excited state, E2 is equal to 4 pi square by 8 ml square. Just to substitute second one, first excited state, N is equal to 2. E1 is equal to 2 square H square by 8 ml square. So we get 4 H square by 8 ml square, that is 4 E1. 4 E1 we can see. For N is equal to 3, for n is equal to 3. That is third energy level or second excited state. That is 9E1. 9E1. So this energy levels, what is this energy levels? E1, E2, and E3. These energy levels, E1, E2, E3, are the discrete energy levels. These energies are quantized in one-dimensional potential box. Each value of En is called eigenvalue, and the corresponding wave function n is called eigenfunction. Thus, inside the box, the particle can only have the discrete energy values. The energies of the particle in a box are quantized. Are quantized. Okay, we are going to discuss a problem. Problem on allowed energy levels. An electron is bounded in one-dimensional box of size 4 into 10 to the power minus 10 meters. What will be its minimum energy? What will be its minimum energy? So you can see here from the given data solution what they are given. So width of the potential box 4 into 10 to the power minus 10 meters. So size or width L is equal to 4 into 10 to the power minus 10 meters. So what is the principle to calculate minimum energy? So En is equal to n square h square by 8 ml square. What about n value? 1. Because they are asking minimum energy. Minimum energy at ground state. Okay. So if n is equal to 1, if we are substituting 1, n is equal to 1, that is E1, 1 square H value 6.626 into 10 to the power minus 34 joule second divided by 8. What about mass of electron? So electron is bounded. So we need to take mass of electron. 9.1 into 10 to the power minus 31 kg into L square 4 into 10 to the power minus 10 meters. So you can write here Planck's constant 6.626 into 10 to the power minus 34 joule second. You remember that value. Mass of electron m is equal to 9.1 into 10 to the power minus 31 kilogram. So we substituted these values in E1 or En is equal to n square h square by 8 ml square. So after calculation, E1 is equal to, we will get 0.03768 into 10 to the power minus 17 joules. So if they will ask in electron volt, we can calculate the electron volts. We need to convert in electron volts. One electron volt is equal to 1.6 into 10 to the power minus 19 joules. From this relation, 1 joule is equal to 1 electron volt divided by 1.6 into 10 to the power minus 19. So here I am taking this is like a 1 joule. So 0.03768 into 10 to the power minus 17 as it is. At the place of 1 joule, I am taking 1 electron volt by 1.6 into 10 to the power minus 19 joules. So E1 value that is 0.02355 into 10 to the power 2 or 10 square electron volts. So this is the problem. An electron is bounded in one dimensional box of size 4 into 10 to the power minus 10 meters. What will be its minimum energy? So the minimum energy in electron volts 0.02355 into 10 square electron volts we calculated. So to try to understand, they gave 2 points. The size or width L, that is 4 into 10 to the power minus 10 meters. So they are asking minimum energy. So N is equal to 1. Calculate the minimum energy. So principle En is equal to n square h square by 8 ml square. E1, n is equal to 1. This is E1, 1 square. Planck's constant value 6.626 into 10 to the power minus 34 by 8 m. This is mass of electron 9.1 into 10 to the power minus 31. This is width 8 ml square. So we need to take here square 4 into 10 to the power minus 2 whole square. After calculation, we get E1 is equal to 0.03768 into 10 to the power minus 17 joules. In electron volts, 0.02355 into 100 or 10 square electron volts. This is the problem. So go to another problem. For your understanding of allowed energy levels, they are asking ground state energy and first two excited states. What is ground state energy? N is equal to 1 ground state energy. We can calculate. First excited, N is equal to 2. First excited state energy. N is equal to 3. Second excited state. We need to understand. So, from the solution, given data, so the width of the box 1 into 10 to the power minus 10 meters given. Find the energy values in the ground state and also first two excited states. Number one, if n is equal to 1, that is called ground state energy. Ground state energy that is E1. We need to calculate E1 value. So formula En is equal to N square H square by 8 ml square. So substituting all the values, E1 is equal to N1 whole square H 6.626 into 10 to the power minus 34 divided by 8. So they are telling electron. You need to remember 9.1 into 10 to the power minus 31 kg. So L square value 1 into 10 to the power minus 10 or simply 10 to the power minus 10 whole square. So after calculation, we can get that is 37.75 electron volts, or I am giving first in joules. In joules, what is that? Joules. So 0.6028 into 10 to the power minus 17. In electron volts, in electron volts, 0.6028 into 10 to the power minus 17 into 1 electron volt by 1.6 into 10 to the power minus 19, you will get in electron volts 37.75 electron volts. That is E1. So what is the E1 value? 37.75 electron volts. Number two, first excited state. First excited state energy. If you can write here, if n is equal to 2, that is first excited state, then calculate E2 value. So we know very well E2 is equal to 4 E1. Substitute 4 into E1 value, how much? You can see here 37.75 electron volts. So E2 value we can get 150.7 electron volts. Next, third one, if n is equal to 3, second excited state energy we can calculate. It is represented by E3. So E3 is equal to 9E1. We know very well. 9 into E1 value 37.75 electron volts, that is equal to 339.075 electron volts. So we can calculate the allowed energy levels like this. Allowed energy level. Okay, next. Allowed energy levels. The first three energy levels E1, E2, E3. That corresponding wave functions psi1, psi2, psi3. That particular probability density functions mod psi1 square, mod psi2 square, mod psi3 square. We can draw a graph of this one. So like this. This is x is equal to 0, x is equal to L, same x is equal to 0, x is equal to L, this is 0, this is L. For example, this is n is equal to 1, it is energy 1. If this is n is equal to 2, this is also n is equal to 2, this is also n is equal to 2. This is energy E2. We know very well E2 is equal to 4E1, 4E1. n is equal to 3, this is E3. So E3 is equal to 9E1. What about this? Along this is x-axis. On y-axis, this is energy graph. Energy graph. So we can discuss along x-axis one-dimensional x, along this y, psi of x or psi. If this is n is equal to 1, this is psi 1. N is equal to 2, this is psi 2. N is equal to 3, this is psi 3. So n is equal to 1, we can observe only one wave. N is equal to 2, we can observe two waves. N is equal to 3, we can observe three waves. Similarly, this is x is equal to 0, n is equal to 1, n is equal to 2, this is n is equal to 3. On x-axis, along one dimensional, that is x-axis, we are taking L value, that width. On y-axis, this is mod psi square. N is equal to 1, we get only one wave. N is equal to 2 mod, so we get only positive wave, two waves. So here also mod, we get only three positive waves. Three positive waves. So you can see here, the energy levels are shown in the figure. N is equal to 1, E1 is equal to h square by 8 ml square. N is equal to 2, E2 is equal to h square by 2 ml square. So E2 is equal to 4 h square by 8 ml square. 4 1 ja, 4 2 ja. So they wrote E2 is equal to 2 ml square. If E3 is equal to 9 h square by 8 ml square, that is 9 E1. Already I discussed. So here, this is E1, this is 4 E1, this is 9 E1, this is 16 E1, and so on. The figure shows the schematic representation of energy levels. It is important to note that the particle cannot have zero energy. The lowest energy allowed for the particle is it cannot possess energy less than this in the one dimensional potential box. The energy value E1 is called 0 point energy. 0 point energy. E1 is equal to h square by 8 ml square. Energy is called 0 point energy. 0 point energy. So the energy levels are shown in the figure below. Already I discussed this previously. So normalization function sin of x root 2 by L sin n pi by L into x. The probability function mod psi square 2 by L sin square n pi by L n pi by L. The energy values of wave function and probability density of first three levels are as shown in this figure. So you can see n is equal to 1, this is energy level 1. N is equal to 2, energy level E2 is equal to 4 E1 or h square by 2 ml square. E3 is equal to 9 E1 or 9 into h square by 8 ml square. So this is n is equal to 1. This is psi 1 already here. So only n is equal to 1, we are observing one wave. N is equal to 2, we are observing two waves. Two waves, one positive and another one negative. If n is equal to 3, we are observing three waves. So if n is equal to n, we can observe n waves. N waves. And magnitude of psi square also, probability density also. N is equal to 1, we have only one wave. N is equal to 2, two waves. Two are positive waves. Why? That is magnitude is there and whole square. So magnitude of psi n square. So this is psi 2, this is psi 3. But what about here? Mod psi 1 square, this is mod psi 2 square, this is mod psi 3 square, psi 3 square. So this is 0, this is L. So this is center, x is equal to L by 2. This is maximum value. This is the maximum value. I am writing here at x is equal to L by 2. If n is equal to 1, at x is equal to L by 2 is max. According to the figure, the probability of finding the particle in its lowest mode, n is equal to 1. Lowest mode, n is equal to 1, n is equal to 1, n is equal to 1. That is called ground state. Is maximum value at x is equal to L by 2. The probability of finding the particle also maximum here. Maximum here, you can see. So for the first excited mode, n is equal to 2. N is equal to 2. N is equal to 2. The probability at the same point is 0. You see, at x is equal to L by 2, this is 0. But x is equal to this is L by 4. This is 3L by 4. It is maximum. It is maximum. Try to understand. I'm explaining this point is maximum. What about this point, midpoint? L by 4. L by 4. So this point is maximum. You can see this point is also maximum. This is minimum. If n is equal to 2, if n is equal to 2, this is x is equal to L by 2. This is center point. X is equal to L by 2. This is the center point. The probability of finding the particle is 0. So here this point is L by 4. This point is 3L by 4. At x is equal to L by 4 and 3L by 4, the probability of finding the particle is maximum. At x is equal to L by 2, 0 or minimum. At x is equal to L by 4 and 3L by 4, it is maximum. It is also clear that the oscillations in the wave function increases with n. Hence, for n tends to infinity, the probability of finding the particle at any value of x lying between 0 and L is almost same. This result is according to the classical mechanics. Thus, the quantum mechanics merges within the classical mechanics at a large value of n. So try to understand here, if n is equal to 1, the psi of x is equal to 1 wave. The mod psi square also 1 wave. But n is equal to 1, at x is equal to L by 2, the probability of finding the particle is maximum. Maximum. So if n is equal to 2, it has 2 waves, psi values. For the probability of finding the particle, if n is equal to 2, x is equal to L by 2, same place, that is the probability of finding the particle minimum or 0. But at x is equal to L by 4 and 3L by 4. L by 4 and 3L by 4. This is L by 4. This is 3L by 4. Up to here, you observe this is L by 4. This center is L by 2. This is 3L by 4. 3L by 4. So similarly, we can observe, it is also clear that the oscillations in the wave function increase with n increases, the oscillations also increases. Hence, for n tends to infinity, the probability of finding the particle at any value of x lying between 0 and L is almost the same. This result is according to the classical mechanics. Thus, the quantum mechanics merges with the classical mechanics at large value of n. So is it clear or shall I explain again? You try to understand. It is very easy to understand. So this center point is, this is 0 to L, 0 plus L by 2. What is that? L by 2. This is a center point L by 2. This point is L by 4. X is equal to L by 4. This is 3L by 4. Try to understand clearly. If n is equal to 1, this energy is given. N is equal to 1, this is psi 1. It has only one wave function. If n is equal to 1, this is psi 1 whole square, psi 1 whole square. So n is equal to 1 at x is equal to L by 2. The probability of finding the particle is maximum. The probability of finding the particle here, this is maximum. If n is equal to 2, this energy E2 is equal to 4E1. This is the first excited state. Here, psi 2, it has two waves, 1 and 2. So mod psi 2 square, if n is equal to 2, at L by 2, x is equal to L by 2, mod psi 2 square, that is probability of finding the particle is 0. X is equal to L by 4 and 3L by 4. The probability of finding the particle, that is mod psi 2 square, is maximum. Similarly, we can understand. It is also clear that the oscillations of the wave function increases with n. Hence, for n tends to infinity, the probability of finding the particle at any value of x lying between this 0 to L, 0 to L is almost same. This result is according to the classical mechanics. Thus, the quantum mechanics merges with the classical mechanics at large values of n values. So these are the energy values here. Energy, take an x-axis, L value on y-axis energy. This is on y-axis wave function or normalized wave function. This is probability of finding the particle, mod psi n square, or probability density. So this is the particle in one-dimensional potential box. We discussed about particle in one-dimensional potential box clearly. So thank you one and all. Thank you.